Hello and welcome everyone to Non IITIAN. If you enjoy the content, please don't forget to like, share, and subscribe to our channel. So, this is a question from TIFR GS 2025, and this problem is on number theory. And the statement of the problem is as follows. Okay, so for a positive integer m, let dm denote the number of divisors of m, including 1 and m. So if you guys have studied number theory, then you know that dm is actually what we conventionally denote as tau m. Okay, define a sequence an by n being the number of elements m 1 less than or equals to m less than or equals to n, such that m has odd number of divisors. Okay, m has odd number of divisors, and we have to find the limit as n tends to infinity of an over n. Okay, now this question is actually very simple once you identify the value of an. Okay, and on a first reading it might not be seeming to be that easy to find the value of an, but actually it's quite easy once you get a bit deeper into it by evaluating the value of dm, the function dm, for an arbitrary natural number. Okay, let's see. So the first question arises is that when is dm an odd number? Okay, so recall that if n is a natural number having its prime factorization as p1 times alpha, p1 to the power alpha 1, p2 to the power alpha 2 till pk to the power alpha k be the unique prime factorization, then dn, which is also as per the conventional notation tau n, is nothing but alpha 1 plus 1 times alpha 2 plus 1, so on and so forth till alpha k plus 1. Okay, now the question is, when is this odd? Okay, right, that is exactly the question, is that when is it odd? So therefore, for such an n, dn is odd if and only if each alpha I plus 1 is odd, right? Because even if one of the factors is even, then the whole product becomes even. Okay, but what does that mean? That means if and only if each alpha I is even. So I can write my alpha I to be, let's say, some 2 times beta I. So therefore, how does my n looks like now? So my n becomes p1 to the power 2 times beta 1, p2 to the power 2 times beta 2, so on and so forth till pk to the power 2 times beta k, but that is nothing but p1 to the power beta 1 times p2 to the power beta 2, so on and so forth till pk to the power beta k whole squared. But then this is nothing but m squared for some m, right, for some m. So therefore what we conclude is that given n in z plus positive integers, dn is odd if and only if n is a perfect square. That's exactly what we required, right? So let me just mark it up. Okay, so therefore, right, so an integer m has an odd number of divisors if and only if m is a perfect square. And this is a very simple example given to us. Now finding an expression for an. So what was our an? So an was the number of elements 1 less than equals to m less than equals to n, such that dm is odd. And by our calculation, we just found out that this is exactly the number of elements 1 less than equals to m less than equals to n, such that m is a perfect square. So what we actually need to find, we need to find all those integers which are perfect square and less than or equal to n, greater than or equal to 1, right? how many such perfect squares should be there? Do I need to actually go for the perfect value? No, I do not exactly require a perfect value. We know that this should be less than or equals to root n, right? So I need to find k squared is less than equals to n, so this implies k must be less than equals to root n, right? I need to find all those values of the form k squared which are less than or equals to n. How many such can exist? At most root n, right? So therefore my an is less than or equals to root n, and it is at least 1, right? Because 1 is obviously a perfect square. And now I hope you guys can already see the answer, right? So do I have an extra page? So I think I give 2 pages for the same thing, but I didn't require it, right? So okay, so the squeeze theorem, now we apply the squeeze theorem. So we conclude that for all n in n, my an is less than or equals to root n greater than or equals to 1, which implies 1 over n is less than or equals to an over n is less than or equals to root n by n, which is nothing but 1 over root n, since limit n tends to infinity 1 upon n equals to 0, which is also the limit as n tends to infinity 1 upon root n. So therefore by squeeze theorem, limit n tends to infinity an upon n is equal to 0, right? So the final conclusion, since an is squeezed between two functions that both approach 0, the limit must also be 0. So you have got your answer, right? So the limit exists and is 0. Thank you for watching. Please like, share and subscribe to Non IITian if you like this video. Meet you guys soon.